Hello and welcome to edupediaworld.com, your favorite portal for online education. And in today's class we will see problems on sequencing. Well, what is a sequencing problem? Basically, it's the problem of finding an optimal sequence of completing a certain number of jobs so as to minimize the total time taken, or the total time between the start of the first and the last job. The idea here is to reduce delays or to reduce the total flow time. Flow time is the total time taken to complete the all set of jobs. We have got different priority rules used to solve these kind of problems, like the first in first out, the last in first out, shortest processing time, earliest due date, and so on. We will basically be focusing on the shortest processing time and the earliest due date. So let's take a question, and initially we will just be working for a single machine. So we have a question here. We have totally 7 jobs, and the processing time of these 7 jobs are mentioned here. We have, these are given in hours: 6 hours for the first job to complete, 4 for the second job to complete, 8 for the third job, and so on. Now if I complete these jobs in the order in which they are here, like if I take up the first job initially, complete it, then take the second and complete, and so on till I go to the last, of course I'll be ending up taking more time to complete the whole set of jobs. Remember, we have got just one machine or one facility to work upon these jobs. So in that case, if I will start my first job at time 0 and I'll be finishing it at time 6. The second job will be the sum of these two. I will of course start at the end of the 6th hour, and I will take 4 hours to complete this. So the total completion time of the second job will be 10 hours. Likewise, the next one would be 18, the next will be 21, the next would be 21 plus 2, that is 23, then 30, and finally 31. So what I see here is that I take a total of 31 hours to complete the last job. Yeah, now this data indicates that this is actually the flow time. Yeah, now this data indicates that my first job will remain in the workshop for 6 hours, the second job will remain in the workshop for 10 hours, and likewise the last job, the 7th job, will have to remain in the workshop for 31 hours. And if I take up the sum of all of these, that happens to be 139 hours, a very long time. And if I want to find the average of these, let me write it here that this is the sum. The average, remember we have 7 jobs, the average would be this divided by 7, and that happens to be 19.85. So on an average, each job has to stay in my workshop for 19.85 hours. Now, do we have a better way, or in other words, can we finish off the jobs in lesser time by keeping them for less amount of time on an average in our workshop? Yeah, we do have, and of course for that we have the shortest processing time rule. The shortest processing time rule says that start with that job which has got the shortest processing time. Now here the shortest processing time, if we look at the jobs, the shortest is for job 7, so we will schedule our job 7 first. The processing time, let me put that here in the second column, for this is 1 hour. The next, which is the next shortest, so this is done. Let me highlight this. Yeah, The next is 2 for job number 5. So job number 5 takes 2 hours to complete. Next is 3 for job number 4. Job number 4 takes 3 hours to complete. Then we have job number 2 taking 4 hours to complete. Job number 2. Next we have is job number 1 taking 6 hours to complete. And we have next is job 6 taking 7 hours to complete, and finally job 3 taking 8 hours to complete. So we have 7 and 8 hours to complete respectively for job number 6 and job number 3. Now if we schedule our jobs in this order, that is 7th job first, then 5th job second job, sorry 4th job second job, 1st, 6th, and finally the 3rd job, we will have the processing times here, and let's see if we have improved upon our flow time or not. So the flow time for the first one will be 1, of course the same one. The next would be, as we have seen, will be the sum of the time we are going to start this plus the time taken to complete this job is 3, and so on. So we complete our 8th job. Again, of course, for true, the last job will have the same timing, because the sum of all of these is going to be 31. But let me see what is the total flow time here. So the sum of this we have the sum coming down drastically from what we had previously. It was 139, the total amount time taken to complete the job, and this time it's just 90 hours. So quite obviously the average also would have come down, so the average would be just 12 hours. So we have improved upon drastically by using the shortest processing time. In the same way, if we have to meet the due date, or in other words, if we have to complete the job within the time given, we use the earliest due date schedule. Let's take a question. Alright, so we have the next question on earliest due date schedule. Now earliest due date schedule is used when we have to complete the job within the due date given for each of the jobs, and this helps us in reducing the number of delayed jobs, or in our terminology we call it as to minimize the tardiness or lateness. Now what is the difference between tardiness and lateness? Well, we may have positive or negative lateness depending on whether we have completed the job earlier or later than the due date. But tardiness, we don't have any negative tardiness. It's only when the job is delayed. So we will be using the term tardiness instead of lateness. Now here we have again 6 jobs each with their processing times, and the due dates are mentioned. So the earliest due date schedule says process that job first which has the earliest due date. So now here when we look at this, we see that there are 2 jobs which has earliest due date, and these are job 2 and job 6, both of these. Now whenever you have a case where you have 2 jobs each having the same due date, what we do is we pick the one which is having the shorter processing time. So here we will have the first one as job 2, and the time taken, processing time for this is 1, and the due date for this job is, say if it is in hours, then it is 3 hours. Similarly, the next job would be job 6 with processing time as 3 and due date as again due date is 3. Next we have is, which is the next due date, and that is job number 1 with 7. So job number 1 which is the processing time is also 1, and the due date is the 7th hour, or if it is day, then it is 7th day. Then we have 8, that is for job number 3. Job number 3, the processing time is 2 and the due date is 8 hours. Then we have is job number 5 with processing time 1 and due date 9. And lastly we have job number 4 with processing time 4 and due date being 12. Now let's see if we are meeting the due date in all of these cases or not. Before that, let's calculate the completion times of these. The completion time of the first one is 1 day. Given the processing time, we start at time 0. The next one would be the completion time of this plus the processing time here, 4 days, and similarly we will have the completion time of all of these. Now let's see if these are on time or not. So if we have to calculate, let me first calculate the tardiness and then lateness, so that you understand the difference between both. Now tardiness, if we have to calculate the tardiness, now we see that the due date of this job was 3rd hour or 3rd day. If in case, let me put this as day, that will be more will be better. Yeah, so the due date was 3rd day and I completed it on the 1st day itself. So am I late? No. So in that case my tardiness is 0. Next, I was supposed to complete this job on the 3rd day, but I completed it on the 4th day. So I am late by 1 day. Sorry, I'm late by 1 day. That's the tardiness here. The next, I was supposed to complete my job on the 7th day and I completed it on the 5th day itself, so I'm not late, no tardiness here. Again here we see that I'm early by a day, so the tardiness value will be 0. Here again we see that we are early by a day, so the tardiness value will be 0, and here we are on time, so again the tardiness value will be 0. Okay, now if we calculate the lateness, as I said, lateness has both the dimensions. It can be positive or negative. So if we look at the first one, the due date was 3rd day, but I completed it on the 1st day itself, so the lateness value here is -2. Or we can just calculate completion time minus the due date. Okay, -2. Similarly here the value was, the completion was done, the job was completed on the 4th day, but the due date was 3rd, so again was late by 1 day. This time it is positive lateness because it was delayed. And the next we see again we are early by 2 days, early by 1 day, early by 1 day, and on time. So these are the lateness values here. Okay, so we have the earliest due date used to minimize the tardiness. We see that there's just one job which was late by 1 day. In case if we would have arranged this according to the processing times, that is shortest processing time, I would have used either job 1 or job 5 or job 1 and then 5 and 2 in the first 3 places. So this would have met its timing, this also would have met its timing, and this also would have met its timing. But then if I would have gone to job 3 being the next in order of processing times, we will have 1 2 3 plus 2 5. This will also meet its timing. Next is job 6, and that would have been late because we see we have already used 1 2 3 4 5, and this will be 8, but the due date was 3. And then finally, of course, this would have met. So in that case, also in this particular question, we have just one problem, which one job which will be delayed, but the amount of time by which it will be delayed would be more. Alright, so that is the earliest due date, and these were the schedules we use for a single machine. Let's move on now to two machine problem and see how to solve. Now in case of two machines job shop scheduling, we use Johnson's rule. Here we have a sample question of 9 jobs A to I, and their processing times on both the machines are given here. This is the processing time on the first machine, and then below that we have the processing time on the second machine. Now what is the rule to process this? The rule says whenever you have two machines job shop scheduling, and we will of course be using the shortest processing time SPT rule, but how do we go about? Well, we pick the shortest the processing time of all of these on both the machines. So we see the shortest is 2 here for A on machine 1. In case if the shortest is on machine 1, we schedule it first, and if the shortest happens to be on machine 2, we will schedule it at the last. So let me put it in graphically like this. Say we have two machines. Let me give them here. You have machine M1 and you have machine M2. Or before that, let me write the schedule first. So if the rule says if the shortest processing time is on machine 1, schedule that job first, and if the shortest processing time is on the second machine, schedule that job at last. So here we see the shortest processing time is on machine 1 for job A. We will schedule it first, so A will be scheduled first. Next, so A is done. We of course don't need to look at 6 also because it has already been scheduled on both of these. So let me just indicate it. Next is, let's see which is the next shortest time, and 5, we have 4, it's 3. Yeah, 3 for job E and job G. So we have both of these. Now when you have two jobs having the same processing time, which one do we schedule first? Well, we look at the other one, that is in here we see that now before that let me just make this clear that these processing times are on machine M2, so these two will have to be scheduled last, but which will be the latest and which will be scheduled before that? So whenever there is a tie, we look into the processing time of the on the other machine, and we see that the other machine, the processing time of E is smaller than the processing time of G. So we will pick E first and then we will go to G. So the next would be job E, and then we will have job G. So here we will have job E will be scheduled at last since the processing time was on the second machine, and then just before that the penultimate job would be job G, because that is also having the same processing time here, and but the processing time on the first machine was larger than the processing time on the second machine. Therefore we will schedule the one which is having the smaller value of on the first machine at the last. Is that clear? Fine. Next, again let's search and see which is the next smallest processing times, and we see that the next smallest processing time is job C having 4 and also job I having 4. So we have now, which one will be we will be scheduling first? Of course we will be scheduling job C first, because on the second machine it has smaller processing time. Yeah, so job C will be processed next in order, and then we will of course be scheduling job I. And where shall we schedule these two? Yeah, we will be scheduling them from the first, because the shortest processing times on these two are on the first machine. So after A we will have job C, and then we will have job I. Well, so what is the next one? 5. So we have B and H again tying up for the next position, and voila, we have the second also. On the second machine also they happen to be tie. So what do we do in this case? Well, we can schedule any one of them earlier and the other one later. We can even interchange them. It's not going to make a difference, because they have got exactly, they are the replica of each other. So it really doesn't matter which one I keep one before. And of course we will have two optimum schedules by interchanging them in both of the schedules. So we can have either say B and H, or we can have H and B. So let's have, either way it doesn't matter. Let's have B and then H, and what are we left with? We are left with D and F. So which would be the next in order? D and F. Well, we see D again has shorter processing time, shortest processing time here on the second machine, and F has got both the processing times higher. So now, since this is on the second machine, what do? We schedule it from the last. So D will be scheduled here, and before that we will have the last one remaining, that is F. So this will be our optimum schedule of the jobs. As I said, we can also have an alternate schedule by interchanging these two, B and H. Yeah, because they have exactly the same values on both the machines. So now let me graphically show this here. I start with the first machine, that is first job, that is job A, and job A takes 2 minutes or 2 hours, 2 units of time on the first machine, and 6 units of time on the second machine. So it takes, let me mark the timings here. Okay, it takes 2 units of time. A takes 2 units of time on machine M1, and then immediately it can be, because machine 2 is vacant, we can immediately take it to the second machine, and it takes 1 2 3 4 5 6 units of time to be completed on machine 2. The next scheduled job is job C. Since machine M1 becomes free at the end of the second unit of time, I can immediately load job C here. Job C takes 4 units of time to complete here, and 7 units of time here. So 4 units, 1 2 3 and 4, it will complete exactly when you have this job completing here. So job C, and then we can load it here for 7 units of time, 1 2 3 4 5 6 7 up to this. This is job C. Next we have is job I. Job I here again takes 4 units of time here and 11 here. So 4 units from here, 1 2 3 and 4 units of time here. And once job I is completed on machine M1, I cannot load it immediately over here, because job C is still under process, and so I will have to wait. In fact, job I will have to wait till job C is is completed, and then job I is loaded. I takes 11 units of time to complete on this. If we go on, say 11 I, and that way we will proceed on both of this. We will complete our graph. Now what is to be observed is that at times the machine could remain idle, as we have the case here. Machine 2 is idle in this case for the first 2 minutes, and sometimes the job will remain idle, as is the case here. Job I was completed at this time, that is 2 plus 6 and then 4 10. I think at the 10th minute it was completed, and then from 10th up to this unit of time, that is 15, I think up to 15th unit of time, it was remaining, it was waiting. So the job I was waiting for this duration. Similarly, we may have at times the jobs waiting, or at times the machine being idle. So at the end we will have to calculate and see what is the flow time. The flow time would be the total time elapsed after loading the first job on machine 1 and unloading the last job from here. So we can either do it graphically as here, or it would be better if we can go to the Excel sheet and calculate them. So let's calculate that here and see. We have the jobs or the tasks. Then we have the processing times on machine M1. Let me first put the task in the order in which I have scheduled them. So first is A, then we have job C, then we have I, the next in order was B, and then we have H, F, D, G, and finally we have is job E. So these were the job. Now we can take directly the processing times of these on both the machines. Let me first put it on machine M1. M1, the processing time, which are given here, and then the time when I'll be loading them, that is time of loading or time for input. Let me put that as in time and out time on machine M1. Similarly, we will have in time and out time on machine M2. So processing time, let's first write the processing time, and here we will get an idea on the amount of time the job or the machine are remaining in the idle or waiting for the jobs. Also we will get the total processing times. So job A has 2 minutes of time. It takes 2 minutes on, or the 2 units of time on machine 1, and 6 units of time on machine 2. Similarly, we have job C having 4 and 7 units of time on these. Job I has 4 and 11 units of time. Job B has 5 and 8 units of time. Job H 5 and 8. Job F takes 8 and 9 units of time. D is 9 and 4. G is 7 and 3, and finally E is 6 and 3. Hope I'm correct. Just have a look. 2, yeah, C is 4, then we have I, that's also 4, B is 5, then 8, 9, 7, 6, yeah. Anyways, so now the in time, of course, since the first machine we have seen is free, the in time would be 0. The out time will be in time plus, sorry, in time is 0. The out time would be in time plus the processing time. so out time will be 2. Similarly, the next job can be loaded directly at 2, and the out time will be 2 plus 4, so no delay in this. And the next will be because this is totally continuous, there is no interruption in between on machine 1, so I'll have straight away the next in time will be 6, as as the next previous job is comes out, the next job can be loaded, and this will be 6 plus 4. Next will be 10, and so on. The in time for the next job will be 15. Yeah, so at the 50th minute machine M1 will be free. Now what about machine 2? The first job can be loaded only when it comes out of the previous machine. So here the first job will be loaded at the end of second minute, and it will come out after it is processed for 6 minutes, that's at the 8th minute. The next job C. Now here we will have to be careful and see whether can I load it at this point. We will also have to look at whether the job is free or not. So here we see the job becomes free at the 6th minute, but the machine becomes free at the 8th minute, so I can only load it at the 8th minute and not at 6th minute. Yeah, and it will come out after it is processed for 7 minutes from 8th minute, so at 15th minute. Now the machine is engaged up to the 15th minute. Although the job is out at 10th minute, the job will have to wait for 5 minutes. So here the next loading time will be 15. Similarly here the out time is 15. So we will have to see which of these two data is actually higher, and that will be the in time on machine 2. So it will be 26 here, and the out time will be 26 plus 8, 34. Next the in time will be 34, out time will be 34 plus 8, 42. The in time will be 42 in this case again. The out time will be 42 plus 9, 51 in time. And at the 61st minute the work will be done, so my total processing time or flow time or the total completion time of the job is 61 minutes. Now what if the idle times are asked for these? Well, the idle time on machine M1, see, we are working for 61 minutes and the machine M1 is free. The workshop is engaged up to the 61st minute, but machine M1 is free at the 50th minute. So if we have to calculate the idle time here, this will be equal to the flow time, the completion time minus the time the first machine is free. So the idle time on the first machine is say 11 hours or 11 minutes. What about the second machine? Second machine, we see the workshop was working from time 0 up to time 61, but machine 2 started its work only at time 2. Therefore the idle time will be the 61 minus 2, sorry, will be 61 minus 59. That is directly the first 2 hours, so I don't have to directly take this, and that is the idle time for the second machine. This of course is the completion time, and if we have to look at individually, the completion time of the first machine is 50, the completion time of the second machine is 61, total completion time of the job is 61. Fine. So, and what about the flow times? Flow times is the total amount of time the work remains in the workshop. So for the first one it is 50, because it starts from 0 and it's completed at 50. But what about second one? Is it 61? No, it's not 61, it's actually 61 minus 2, because for the first 2 minutes there was nothing in this workshop. So this is the flow time, the completion time, and the idle time. So that is the calculation for this problem, and this rule is called as the Johnson's rule of scheduling for 2 machine job shop problems. Well, that's all we have for now on job shop scheduling. We will continue this topic later on with other scheduling problems.